fundamental counting principle. Putting the fun back in fundamental counting principle. Okay, so we're going to learn how to count. But in a slightly different way, they're just sort of 1, 2, 3, right? Because what we want to count can happen many different ways. We want a quick way to get there. But we'll start off with the slow way to get there. So, the iPad mini was released in the fall of 2012 in either black or white, as Wi-Fi only or Wi-Fi cellular. And both models came with 16, 32, or 64 gigabytes of memory. Use a tree diagram to show the sample space. So a sample space is all the possible outcomes, right? Like it's every possible model that we could have bought. So the sample space is a list of all possible outcomes. Or in this case, be a list of all possible iPad minis. Possible iPad. And sometimes a tree diagram is helpful, right? You're going to make a decision, and you want to buy a car, and it could be the same deal. You can get the sport, the sedan or the hatchback, and maybe there's two different colors. Though in Henry Ford's day, it was any color you want, as long as it's black. And different size, different options, right? So that's basically what we're doing. Is sort of, we're going to enumerate them. We're going to list them all. So here's how we do a tree diagram. It's kind of actually a fallen tree, really, because it's on its side. And it branches out, right? So for the iPad mini, we say, well, you got a color choice, right? It could be black. Or, hang on, it's going to shrink this down a bit. And it's going to 125. Could be black. Let's not go quite that tall. So it's black or white. If it's black, then what kind of model could we get? So we could get Wi-Fi or cellular. If it's white, what model can we get? Wi-Fi or cellular. If it's black and it has Wi-Fi, what memory possibilities are there? Okay, so 16 or 32, so we're branching off from there, or 64. If it's black and it's cellular, what kind of memory can we get? So 16 or 32 or 64. If it's white and it's Wi-Fi, what kind of memory can we get? 16 or 32 or 64. And if it's white and it's cellular. Now, if we follow each branch in this diagram, so it's called tree diagrams because it branches out. If we follow each branch, then we can list. So follow the branch, we've got black, Wi-Fi, 16. So black, Wi-Fi, 16. We've got black, Wi-Fi, 32. We've got black, Wi-Fi, 64. We've got black, cellular. Now, if I asked you to list these, you probably could list them, right? You start off by listing a few. This gives us a way to do a systematic way to do it, right? So we're not going to miss anything. Otherwise, at the end, if you're just listing them yourself, you're kind of like, did I get everything here? Right? Have I taken all of, you're counting through your list, and then you're trying to think how many should there be, right? If I'm going to list them all, I have to know how many there are. But this is systematic, right? So it could be black. So this is all the blacks, right? Up here, everything's black. Here, everything's black Wi-Fi. Okay. So we got black, cellular 16, black, cellular 32, black, cellular 64. Then we go down. This is all the possible black models, right? So now we do that same thing for the white. So we've got white, white Wi-Fi, 16, white, Wi-Fi 32, white, Wi-Fi 64, white, cellular 16, white, cellular 32, white, cellular 64. So the number of different possible iPad mini tabs to be purchased is 1, 2, 3, 6, 7, 12. Okay, got 12. This number can also be found by determining the product. So what? What can we multiply together to get 12? So color, we got two choices. Model, we got two choices. Memory, we've got three choices. And 2 times 2 times 3. So 2 times 2 times 3 is 12. So if we don't have to list the sample space, but I only want to know how many models, then I just say, well, you've got two choices per color. For each of those two choices, you now have two choices, right, which would be 4. So if we ignored memory, so, okay, you got black Wi-Fi, black cellular, white Wi-Fi, white cellular. And for each of those 4 choices, we then have 3 further choices for the memory. So 4 times 3 is 12.
What if the white doesn't have 64 gigabytes?
Then that would be special, and we would take those off, right? Then you'd need to use a tree diagram, right? You couldn't just use this 2 times 2 times 3, because it's no longer, well, it's 3 if it's black, so then we could just figure the black figured out, just say, okay, black, that's just 1. So for black, we've got 2 times 3, which gives me 6, and then for white, we'd have to pretty much do the tree diagram, and then cross these off and not list them. Okay, so then you'd need a tree. So you might want this just so you say, well, I just want to look at all the possible things that I can have, right? Maybe we don't need to list them all. Okay, we just need to know that there are 12 types. When Apple's manufacturing these, they're going to try and sort of figure what's the demand. You know, oh, we think there'll be less demand for the 64 gig. There'll be less demand for cellular than Wi-Fi products, more expensive. There'll be less demand for 64 gig than, say, 32. Maybe the sweet spot is 32, right? But 16 is not, not enough. And then they'll manufacture based on that. And then as the orders come in, they'll modify, right? Just say, and that's, any manufacturer has to make those decisions, right? How many of this model are we going to sell? How many of the different colors? For Samsung, it's like, what color did Apple release? We have to make one of those now, right? Like, let's follow. Anyway, if one item can be chosen in M ways and a second item can be chosen in N ways, then both items can be chosen in, what do we do with the numbers? Multiply them together, right? M times N. So we have 2 models in 3 different colors, and there are 6 choices, right? You're going to have model A in red, in green, in blue, whatever. That's called the fundamental counting principle. So now let's use it. So we're going to do a whole pile of examples here. Let's make this bigger now. An upscale restaurant offers only 3 choices for appetizer, 4 main courses, and 2 different desserts. If a customer chooses exactly 1 appetizer, 1 main course, and 1 dessert for a complete meal, then determine the number of different meals the customer can choose. Okay, so here's how you do a fundamental counting principle problem. You say, I've got appetizer, main course, dessert. Appetizer, main course, dessert. So you list your choices as blanks. You put multiplication symbols in between them. And if you want, you can just write below, this is what it is, right? Appetizers. Okay, so how many choices for appetizer? 3. For the main course and for dessert. And so overall, 24. Okay. So if you went back to that same restaurant every day for a month, you could go 24 days before you had to repeat a meal. And it's upscale, so you hope to have lots of money, or you could be pretty poor. But okay, determine the number of ways the letters of each of the following words. So we like to do arrangements of letters in words, right? Because we're counting, right? We're saying how many. So how many ways are there of arranging the letters in the word math? So how many letters are there? 4. So fundamental counting principle, I like to put down 4 blanks. Now underneath, I could write first letter, second letter. I'm not going to. Okay, it's kind of different. With appetizer, main course, dessert makes a little more sense. Okay, so the first letter, how many choices do I have for the first letter? 4, right? We could choose any of. Once the first letter has been chosen, then how many left for the second letter? 3. And that's equal to 24. Okay, do the same deal. Factor. Okay, don't factor, but figure out the arrangements of. You can't take out an F because it's not common. And when you're arranging letters and words, pretend they're on Scrabble tiles. You've got them in front of you, and it's like, okay, so I've got, and then. Okay, is that what you got? So 6 choices for the first letter, then 5, then 4, then 3, then 2, then 1, right? So it's a pretty boring unit so far, right? But kind of nice, because it's nice to be bored, right? It's like, there are no transformations in this, other than maybe ask you how many ways you could arrange the letters in the word transformations. There's no transformations here, right? It's something completely different, and concept that you're pretty familiar with. Like, we're all pretty familiar with kind of arranging things, right? And now we just sort of need to think about this. Based on the answers to question 2 and the chart shown to the right, and answer based on answer the following question. What function does exclamation mark perform on the number? So here's a chart. 1 exclamation mark, which is read as factorial. Okay, so the exclamation mark is read as factorial, or you just say it in a very excited tone of voice, like 2. Not 2, but 2. With the implied exclamation mark. 6! Not 6. 6! Okay. Or we say 6 factorial so that if we actually read this. So 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, and so on. So what does the factorial say to do? Yep.
You're taking the numbers under that and multiplying by each other.
Okay, so you're multiplying all the numbers.
Under the numbers.
You're including the number that's got the. Okay, so you're going to start with the number and multiply. So it's just like we did with math, right? 4 times 3 times 2 times 1. Or factor. 6 times 5 times 4 times 3 times 2 times 1. Right? That's where we got 720. Only you were going 6 times. Because I haven't shown you yet where on the calculator the exclamation mark is, right? But we will. Okay, so what function does the factorial do on a number? It multiplies that number, so finds the product of that number and all subsequent lower natural numbers. Because it's got to end at 1, right? So we did math. It was 4 times 3 times 2 times 1. We did factor. It was 6 times 5 times 4 times 3 times 2 times 1. So what's the value of 8 factorial? So how can you find that? What's a quick way? So you could go 8 times 7 times 6 times. I don't think that's all that fast. So what's a quick way? Okay, but if you didn't know that,
8 times 5,000.
Yeah, you could just say, well, if 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1, and I want 8 factorial, which is 8 times 7 times 6 times 7, wait a second, I already know what 7 times 6 times 5 times 4 times 3 times 2 times 1 is, so I just multiply this by 8. Right? So 8 factorial is just 8 times 7 factorial. Okay. Or 8 factorial is 8 times 7 times 6 factorial. Or 8 factorial is 8 times 7 times 6 times 5 factorial, right? So if I get tired of writing, I just stop and throw down an exclamation point, so I'm done, right? 8 factorial is 8, right? This is 8 times 7. So we know it's this. But I'm lazy, and you already told me what this was, right, in your little chart there. So I'm just going to write it 8 times 7 factorial. Okay, what's an expression for n factorial? Where do we start?
N.
N.
N minus 1.
N minus 1. And where do we end? Now we're going to end off with 3 times 2 times 1. This presumes that n is greater than 3, but you've got the idea, right? You're just going to start with a number, multiply it by the next lower number, by the next lower number, and so on. Okay, what's 100 factorial over 98 factorial? Because here's the question, right? So somebody said, hey, we found the factorial, right? Where's factorial? It's under math, right? So get your calculator out. You want to see this? Okay, so I want 8 factorial, so I'm just going to hit clear. 8 math. Okay, if you've got who has a frac on the end there? Okay, so not many. It'll only be the color calculators that have the frac. So right on the end, you've got PRB, right? Doesn't even say PROB. It says PRB. Fastest way to get there is one left arrow. Okay, I have to go 2 because I got that frac there. And then 4. Okay, but first I actually have to give the number. So I need to get out. Oh, I did the 8. Okay, so I go 8. I go math over to PRB, hit a 4, throws in the factorial, right? So now it's 8. Hit enter, dramatically get the little dot there, clear the little dot there, and we get 4,320. Okay, so you want 100 math. Wrong one. And it says too big. Too big. It says calculation exceeds the range of values this machine is able to display. So okay, we're stuck then, right? So we can't work it out. Yeah.
So what's the biggest value?
Oh, I don't know. Play with it and figure it out. Yep.
So it'll be 100 times 99 times 98 factorial, right?
Oh, so 100 times 99 times 98. I'm getting tired, so I'm going to stop now. Okay, why am I getting tired? Because I've got a 98 factorial on the bottom, right? So I can expand a factorial, and anytime I want to stop, what do? I put down the factorial equivalent of a stop sign, which is the exclamation point, right? Click, I'm done. Okay, and where do I stop? I stop when I'm matching what's on the bottom. Why? Because what's 98 factorial divided by 98 factorial? 1. What's 99 times 100? 9,900. So your calculator is useless, right? Won't do 100 factorial, won't do 98 factorial. I don't know what the largest is, but somebody's going to play with it and tell us at some point. Rewrite the answers to question 2 in factorial notation. Okay, so 4 times 3 times 2 times 1 is? And 6 times 5 times 4 times 3 times 2 times 1 is? 6 factorial, right? So are we ever going to punch into our calculator 6 times 5 times 4 times? No, right? Doesn't make any sense. We're going to punch in 100 times 99 times 5. No, we're going to say, wait a sec. Let's use our brains here. In general, there are n factorial ways to arrange n items. Okay. Now that we know about factorials, let's do some more examples, and where appropriate, leave the answers in terms of factorials. Okay. So here, big point. This unit's called Combinatorics. Sometimes the answer will be in what we're going to refer to as Combinatorics notation, right? Which means we're not going to work out a value. We're just going to leave it written as factorials or the other stuff that we're going to learn. So you need to be able to look at an answer. So this is what you want. Before you do a multiple choice question, you want to look at the answers. Okay? And not because, you know, but it's a spoiler, right? I want to cover them up and come up with my own. But just to know what form my answer should be in, right? Like if you look and say, oh, the answer is in this notation, it means I'm not going to get the answer in this notation and then work it out to a number, right? It's like, that's a waste of time. Okay? Nobody cares what that number is. They don't. They didn't list the numbers, so there's no point in me going on and working out a number if I don't have to. How many ways can 5 teachers and 10 students be lined up if there must be a teacher at both ends of the line? You really have to think about things before you answer, seriously. So in this unit, if no other, you really have to think about things. If you just leap in and say, oh, 5 factorial, 10 factorial, you're going to get everything wrong, right? Like it will seriously be, everything will be wrong. So combinatorics, you got to sit down and say, okay, what do they mean? What do we got going on here? So how many people am I lining up? You're going to line up 15. So I'm going overboard, but I could list the 15 items, and I'm going to, right? I'm going to go a little overboard, and then once we've done a few, you'll look at it and say, right, okay, I know what to do here. Okay, and like I don't need to write out 15 things, but I'm going to write out 15 things. 1, 2, 3, 4, 5, 7, 8, 9, 11, 13, 15. Hopefully that's 15. 15. Okay. Now, here's the deal. That's fundamental counting principle, right? I am arranging 15 objects. But when you use fundamental counting principle, sometimes you have restrictions to deal with. What are our restrictions?
Teacher at both ends.
Got to be a teacher at both ends, right? So, must be a teacher here and a teacher here. All right, how many teachers are there to choose from that go in this spot? You know, 5 teachers. Any one of those 5 can go here. How many teachers are remaining that can go on the end of the line? 4. How many people do we have left to arrange in here? 13. Do we care? Okay, so at this point we are no longer distinguishing, right? It's like I have 15 people, but you 5 teachers. Well, you're special right now because I need one of you here. Okay, so one of the 5. Oh, and I need one of the 4 remaining here. Okay, the rest of you line up. So how many ways can 13 people line up? It's like somebody's lost wondering the hell. What's this number? So it's 13 factorial times 20, right? Or 20 times 13 factorial. Push me over with a feather, Dave.
Thank you.
Anybody else wouldn't care about it. I gotta remember to give her this. It's a little fee.
Okay, people fun. Thanks.
Okay. So subsequently, if we do this, you just got to think, okay, look, got to put a teacher there, and I need a teacher here, and then I got 13 people, or I'm sorry, teacher, right? And you can sort of condense it to that, right? But I'm showing, here's the full thing, right? And it's just so we can see, that's the full thing, right? We dealt with these guys, now there's 13 left. That's just 13 factorial, right? How do we arrange n objects? How many arrangements can be made? So now here we're just going to have a number of different ways, from no restrictions to everything begins with a J, etc. Using all the letters in the word Jasper, if no letters can be repeated. So whenever you're arranging letters in a word, again, just pretend they're on Scrabble tiles, they're sitting in front of you, you're going to pick a tile off, put it down, it means you can't repeat that letter, right? So if there are no further restrictions, we know how to do that. How many letters? So 6. How many ways can I arrange 6 letters? 6 factorial, or 720, right? You could write out the 6 blanks and that, but for this one, I don't think you need to, right? 6 arrangements together.
If it doesn't say how it wants it, does it need to be like exact values?
Uh,
The one above we left it.
so if it's numeric response,
Yeah.
number. If it's multiple choice, look and see what form it's in.
And
And if it's written, then we're probably going to tell you rounded. Well, the arrangements are all natural numbers, right? It's not like, hey, rounded to the nearest tenth. It's like, what tenth? You can't have tenths.
yeah.
Okay. The arrangement must begin with a J. So how are we going to handle must begin with a J?
5.
Yeah, so what do you think? What do I do with the J? Just toss it, right? So here's my letters. J, A, S, P, E, R. Okay, you're out of there. What's left? 5 factorial, 5 letters, 5 factorial. Okay, which is... Now, here, I'll show you fundamental counting principle as well, because why not? So 6 choices, then 5, then 4, then 3, then 2, then 1. Here, 6 blanks again, right? It's always 6 letters that are being arranged. So this is a J. There's one way, then 5, 4, 3, 2, 1. Okay? And I think actually, you know what, it can't hurt to show it both ways. It just gets us used to, if they're given answer in factorial notation, we can at least look at it and say, why do they have 1 times 5 times, oh, because they use fundamental counting principle. P and R must be in the middle of each arrangement. So P and R. All right, so we do have a middle, right? We've got 1, 2, 1, 2, 3, 4, 5, 6. We got 6. Okay, how many choices do you have for the first letter? 4, right? It could be a J, an A, an S, or an E, right? So you have 4 choices for the first letter. How many choices for the next letter? 3, right? So this is J, A, S, E. How many choices for the next letter? So P or R. So 2, right? It could be the P, it could be the R. How many choices for the next letter? 1. If you put the P there, you got to put the R there. If you put the R there, you got to put the P there, right? So it's P, R, or R. 1. How many choices for the second last letter? There's 2 left, and then 1. So this one, you can't use factorials really. Well, you sort of can, because you can say, look, I'm arranging 4 letters, right? J, A, S, E, and then I'm arranging another 2 letters. So this works out to 48. Okay, and then you could say, well, you know, I could think of this as, you know, I'm doing 4 factorial and 2 factorial. Okay. Now, in that case, does it really matter if they were in the middle? What if they were on the end? Wouldn't make any difference. What if they were the first 2 letters? Wouldn't make any difference, right? There'd still be 48 ways to arrange them. So the fact, what if they were the first letter and the 5th letter? Wouldn't make any difference, right? You're still going to say, well, that's got to be a P or an R, and then, so I go here because it has to be a P or R, then I go here because it has to be the remaining one, and then it's, okay, and then it's 4, 3. Okay, so it's 4 factorial, 2 factorial. A consonant must be on each end. Again, easiest way to do this, to me, fundamental counting principles, put down 6 blanks. 2, 4, sorry, let's have 6 blanks. Okay. So you got to have a consonant here and a consonant here. So that's not a C, it's a consonant you have to take context into. How many consonants are there to choose from? 4. Okay. How many consonants are left that go here? 3. How many letters are left? 4. So then this becomes 4, 3, 2, 1. Okay. So it's like 12 times 4 factorial. Okay, which is 240 and 48. 288. Now, I mean, you can think of it as well, you know, I've got these guys, that's 4 factorial, then multiply by 4 and 3. This is the easiest way to do this, okay? If they have numbers, do this, work it out, get the number, see the 288, go, matches up with what I got. And that's another way you might want to do it. If it's all numbers, just like do it, get your number, and then look and see if your number's there. If it's not, you mess something up maybe. The consonants are together. So J, A, S, J, A, S, P, E, R. The consonants are together. So here's how I would do this one. Think about the consonants are on one tile. But then, wait a sec, can they move around on that tile? Yeah, because they don't have to be in order, like J, you know, they're not in alphabetical order, it's just they're together. So think of this as, here's one tile, and here's a second tile, and here's a third tile. So how many ways can I arrange those 3 tiles? 3 factorial ways, right? But one of those tiles has 4 things on it, which could be arranged how many ways? 4. So it's 3 factorial times 4 factorial. Okay, so 3 factorial because we are arranging 3 things. But one of those things has 4 arrangements, right? For every one of those, what's 3 factorial? It's like 6, right? For every one of those 6 arrangements, I could have JSPR, or I could have JPSR, or, you know, I have 4 factorial ways of doing that. So for every one of those 6 arrangements, there are 4 factorial, 24 ways of arranging the J, S, P, and R, and that gives me, whatever, 644? 144. The vowels are together. Okay, so what do we do here? J, S, P, R. You guys are now each on your own individual tiles, but what do we do with the vowels? We put them together. So how many tiles do I have to arrange? 5 of them. But one of those tiles has 2 arrangements, right? So 2 factorial arrangements. One of those tiles, because it says vowels are together, but it says not in order, right? Like if it said the vowels are together in alphabetical order, then it's just, okay, it's AE, right? You can glue them together. Every arrangement is going to have an AE. So this is 240. Yeah? The vowels are not together. Okay, that's a bit tougher, right? I don't want the vowels to be together. So that means, well, okay, so my first letter could be a vowel, and then I need a consonant, and then the second one could be a vowel. I could have a vowel and then 2 consonants. And if you start thinking about how many ways they can't be together, you're going to have to sit down and think about a lot of, well, okay, it could be first and third, it could be first and fourth, it could be first and fifth, it could be first and sixth, it could be second and fourth, it could be second and, right? That's a lot, right? Like, we really have to go through each of those. But we can say, hang on a sec. If there are no restrictions, how many arrangements are there? Look on your sheet. No restrictions. There are 720 ways with no restrictions. How many of those ways have the vowels together? So how many of those ways do not have the vowels together? 720 minus 240. So I already have the numbers there. Right? Where's that? 480, 480. To directly count the vowels are not together, you would have to examine a whole pile of different scenarios, right? And it's not worth it. So instead, you look for another way around the question, right? I know how many arrangements there are without regards to order, 720. Now, how many of those have the vowels together? 240, which means that the rest of them, the vowels are not together, right? Easy. Consonants are in the same order as they are in Jasper. Okay, how are we going to do this one? Okay, it's arrangements of A and E. How many ways can that be done? Not quite. So think about this. Yeah, it can't be 2. Right? You can think of the third immediately, right? I could have the JSPRAE, JSPREA, and JAS. Well, there's Jasper. That's one arrangement. Okay. So let's think about it. I have 6 blanks. So I'm only really interested in putting the vowels down, right? Like once the vowels are down, there's only one way to fill in the rest of the blanks, yeah? It's got to be a J, and then an S, and then a P, and then an R. So how many ways in here can I put those 2 vowels down? Okay, how many choices do I have to put down the A? Yeah. Where can I put the A? How many spaces? There's 6 spots available, right? So I can put the A in any one of 6 spots. Where can I put the E? In any one of the 5 remaining spots. Where do the JSPR go? They go in order where they have to. So at that point, so if I put the A here and the E here, then it's got to be JSPR. If I put the A here and the E here, it's got to be JSPR, right? Like there are no more choices after that. I have no choice. I have to put them down in order. So it's like 6 times 5, and then times 1 times 1 times 1 times 1. So it's just 30 different ways. So it's easier just to think about, instead of saying, well, I got to put the consonants down, just say, no, really, my only choice is where do I put vowels? Okay, I got 6 blanks available. I can put that A in any one of those 6 spots, or the E. And I can put the E in any one of the 5 remaining spots, or the A. How many 3-digit numbers can be made? So what's the deal with a 3-digit number? Is 079 a 3-digit number? No, it's a 2-digit number. So Three-digit numbers. So so numbers can't begin with a 0. Okay? So however many digit numbers, it can't begin with a 0. Now if it's a passcode, then sure, right? You can start with 0. Like 079 might be a valid passcode on something, or a combination. You see those combination locks that have just like the 10 digits and you just sort of rotate them around? Okay. All right, so how many three-digit numbers can be made if the digits can be repeated? So, three-digit number, 1, 2, 3. How many choices do I have for the first digit? First of all, how many digits are there? 10. There are 10 digits, right? 0, 1, 2, 3, 4, 5. We'll just be talking about on two normal things. How many digits are there? There's 10. There's 10 digits, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. How many choices do we have for the first number? 9. Because? Yeah, so cannot be 0. There are 9 choices. Okay? So, in first place goes 1, 2, 3, 4, 5, 6, 7, 8, or 9. How many choices do I have for the second digit? Okay? So I can repeat, so 10 digits, right? Because I can put a 0 in there, that's fine. How many choices do I have for the third digit? 10. How many ways are there? 900. So there are 900 three-digit numbers ranging from 100 to, well, you can repeat, so never mind. Oh, no, those are repeating, yeah. So 100 to 999, right? So there'd be 100 or 900 numbers. Okay, digits cannot be repeated. Repeating is boring, right? I mean, it's just like, what's the restriction in that? If you can't repeat and there are no further restrictions, how many choices? So, first of all, what's the inbuilt restriction? Cannot begin with a 0, right? So no further restrictions mean, okay, there's a restriction. So how many choices do I have for the first digit? Okay, so it can't be 0. This will be 0. Okay, you got 9. How many choices do you have for the second digit? Okay, so here's 10 digits, right? First choice, I have 9 choices, right? Because I can't do the 0. Okay, so this comes back in now, right? So the 0 was out, but now it's back in. So how many choices for the second digit? 9. And then 8. What's that? 648? That's almost that lottery where you have to arrange numbers. It's close, but not quite. Okay, so think about this. I got 10 digits, can't be a 0, there are 9 choices. I choose one of those 9, but now the 0 comes back in, right? I'm allowed to have. So now I have 9 choices. And then one of them's gone, now there are 8. The numbers must be greater than 600. Okay, what's the restriction if a number has to be greater than 600? So the first number has to be what? 6, 7, 8, or 9. So the first number has to be 6 or greater. How many choices are there for that? 4. Okay, so greater than or equal to 6, first number. No, you don't have to worry about 0 being out front. Okay. Now I can't repeat digits. Okay, so again, so I got 10 digits. I have chosen one of them. How many are left for the second spot? Or sorry, I've chosen from the 4. Okay, so now everybody comes back into play. 1 is gone, so now there's 9. And then, how many choices? 8. That 72 times 4?
Yeah, it would be 7, because if you had like 600,
Can't have 600. You can't repeat digits.
yes, that would be 7.
Can't repeat digits. You can't have 600. Right? So if you have a 6 here, you can have a 0, but then it's going to be a 1. So it has to be greater than 600. If there's a 6 in front, you cannot have 600. Right? Because that would be repeating zeros. You can't repeat. So the lowest number you could have is 601. The highest number you could have is 9, 8, 7, I guess, right? Because you can't repeat digits. Okay, make sense? What is that? 288? That number comes up a lot. The number must be odd. What makes a number odd? Not even. Good. What makes a number not even? It's odd. Okay, we're going in circles here. What makes a number odd? The last digit. What must the last digit be for a number to be odd? Not divisible by 2, or in other words, odd. So, an odd number has to have an odd last digit, right? That's our first restriction. I must ensure this number is odd. So how many choices? So this digit must be odd. Must be odd. How many odd digits are there to choose from? 5, right? It's a 1, a 3, a 5, a 7, or a 9. So we have 5 choices. Now we go to first place, and we say, well, what do we say to the first digit? First number. You can't be 0, right? Okay, so wait, let's think about this. Here are the odds. Here are the even digits, and this one is 0. Okay. So first off, I say, okay, it's got to be odd. I have 5 choices, right? One of them has now been chosen. There are now 4 remaining odd digits. In come the evens, but you say you can't pick you, right? So how many choices do I now have for the first digit? 8. Okay, I've used up one of the 10, right? That's the odd. I put an odd digit down. So I have 9 digits left, but 0 is one of those 9. It can't be in there, so there's 8. Okay, I have 10 digits, 1 is odd, and 0, this goes in, and the 0 comes back, so how many choices are there for the third? There are 10 digits in total, I've used 2. There are 8 remaining. Okay, because at this point there's no restriction on this, right? So there are 10 digits, one of them got used up, an odd one got used up here, leaving me with 9. I went here, and I said, I got a choice of 9. Oh, but you can't be 0, so I have a choice of 8. Okay, now I've used up 2 of the 10 digits, and now I come here. So there's no restrictions now, and I've used 2 out of 10. There are 8 remaining. Okay? And that's not 288. 320. Yeah? Says what? The numbers must be odd. No, it means the number. Can I repeat it? And it's a 3-digit number, so they're saying 3-digit numbers can be made. So all of the 3-digit numbers must be odd.
Well, I guess if it said the digits must be odd.
You cross off the S if it makes you feel better. The number, or numbers, whatever your comfort level allows you, must be even. So, what makes a number even? Don't say it's not odd. Okay, I don't know about this. So, by the baseball diamond. Okay? Go, leave your stuff. Go, now. Go, 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 go. This is not during a test. Keep going. I don't know that this is a drill. I would like to not learn. So. No, I seriously, if there was one, it's not in my phone would have buzzed. No. There's a problem if the number is even, right? Because if it's even, what does it end in? 0, 2, 4, 6, 8. But if it ends in 0, then we don't have to worry about it beginning with 0. So we have to do 2 separate cases, right? So we've got, so ends in 0. That makes it even. How many zeros are there from which to choose? 1. Okay, now, we don't have to worry about this one being a 0, so how many choices do we have here? 9, and then 8. So that's 72. But there's ends in 2, 4, 6, or 8. And then this one can't be 0. So how many 2, 4, 6, 8? We have 4 choices, right? Okay, I've used up one number. I have 9 left, but one of them is 0, so how many choices? We have 8. I've used up 2 numbers. We have 8 left, so it's 8 times 8 times 4, right? Which is 64 times 4, which is 256. And then we add those together. 8 to 328. But wait a sec, you say. Or you would if I gave you time, which we don't have. But look, there's 648 possible numbers. If 320 of them are odd, then what do we know about the rest of them? They're even. So you don't do this. You say, wait, let's take all numbers minus the odd numbers. Oh, you can do this, right? Minus the odd numbers. So it's 648 minus 320, and we get our 328. Now, if you look at it, this is tough, right? Because first you have to realize, wait, there's two cases, right? It could be a 0, and then, so you have to work out like two kind of tough scenarios. This is easy, right? You can't lead with a 0, so 998. This one's easy, relatively, right? Just this has to be odd, and after that, just sort of the normal. So these two guys are pretty easy to figure out. So if you have to do evens, do all, and then do odd, and then subtract. Okay? It's a lot easier than doing the kid, right? That'd be like the Jasper with the vowels, whatever. What were they? The last scenario, the vowels are not together. You could work out, right? There's like a whole pile of different cases where they're not. It's like first and third, or first and fourth, or first and fifth. Right? You don't want to do that. And for here, you can do this. It's not terribly bad. But 10 different books comprised of 3 math books, 2 chem books, 4 bio books, and 1 physics book are to be arranged on a bookshelf. Okay, if you want to arrange 10 books on a bookshelf, and we just say go for it, how many ways are there? You may express that in factorial notation. 10. No, not 10. There's 10. Right, which is actually a pretty large number. Which I should have written down. But you could figure out too, right? Because you just do it on your... So that's 3,628,800. That's like a lot of weight, right? If you just think about it, like I'm just putting 10 books on a bookshelf, and I can do that over 3 million ways. What if the 2 chem books must be on either end? So now, just think about this. So I got a chemistry book here. How many ways can I put a chemistry book here? 2. How many chem books do I have left to go on the other end? And how many books are in the middle? And how are they arranged? Okay, so it's 2 times 8 factorial. Right? This time we're not writing out the 10 different blanks, right? We just say, hey, wait, we've done that. That's like the teachers on either end. Okay, in this case, it's chem books. So 8 factorial, we worked out was what, 40,000 something. So this is 80,000. So was it 320 or so this would be 640? 640? 80,600. The math books must be kept together because they get lonely if they are like math. We stick together in math, right? It's not, chemistry, it's you have things that repel in chemistry, right? So there's math that's grouped together. So. Math books must be kept together. So how many math books do we have? 3. So here's my 3 math books, right? That's 3 factorial. How many other books are left? So there's 7 other books. So how many things are we arranging then? I got 7 books and I got this group of 3 math books. Let's take that out for now. Let's just call this math. Okay, so how many books, in quotes, am I arranging? 8. But one of those groups can be arranged how many ways? So I'm arranging 8 objects in a sense, but one of those objects is the 3 math books, which can then be juggled in order, right, 3 factorial ways. So it's 8 factorial times 3 factorial, which is 241,920. The 2 chem books cannot be together, right? It's a chemical thing. Things that repel in chemistry, right? I think. It's magnetism in physics, but aren't there chemical bonds that aren't bonds, but the opposite? I don't know. The last time I did chemistry was 1970 something. I have no idea. So the 2 chem books cannot be together. What's easier to work out? Wouldn't it be easier to work out the 2 chem books are together and then just subtract that from all the possible arrangements? So it's going to be 10 factorial minus the chem books are together. All are together. So how many ways can the chem books be together? Okay, so hang on. So we got 2 chem books and how many other books? 8. So in essence, we're arranging how many objects? Air quotes, objects. We're arranging 9 objects, right? The 2 chem books are one object, the 8 other books. So we're arranging 9 objects, but 2 of them are chem books, and they can be arranged how many ways? 2 factorial. So it's 10 factorial minus 9 factorial, 2 factorial. Likely, that would probably just be left in that notation, right? And as a multiple choice, you would just see a bunch of notations. But if you actually want to work it out, it's 2,903,040. Okay? Because to do the chem books can't be together, it's the same deal. Right? Well, first you could have a chem book, and then you could have, right? And there's too many ways to do that. It's much easier to say, wait, well, we just did math books together, let's just do chem books together. The books must be in the order math, chem, bio, and physics as seen from left to right. Okay, so we got math, chem, bio, physics. Math, chem. How many ways are there of arranging the math books? How many math books are there? 3. So there are 3 factorial arrangements of math books. For each one of those, there are 2 factorial arrangements of chem books, right? There are 2 of those. I can't remember how many bio and physics. 4 bio and 1 physics. And then the 1 physics. So it's 3 factorial times 2 factorial times 4 factorial times 1. Right? So we've got the math, but there's 6 ways to arrange those. For each of those 6 arrangements, there's 2 ways of doing the chem, and for each of those, there's 24 ways. So it's 6 times 2, which is 12, times 24, which is like 240 and another 40. Is that 288 again? 288. Number keeps coming up. The subjects must be kept together. So now it's really these 288 ways, right? Okay, so the math is together, the chem is together, the bio is together, and physics really only rates 1 book anyway, so physics. But now they're together, but how many orders can they be in?
4 factorial.
So we're going to go 4 factorial times. So this is them together, but in one particular order. And then we say, but wait a sec, they can be in any one of 4 orders, right? It could be math and chem, then bio, then physics, or math, and so on. Okay, so it's 288 times 24, which I can't possibly do. So it's 6,912. I will edit this down because you might want to come back and look at it because you're not even going to know what this. Where did the 4 factorial come from? Why is, so I will edit out the blank spot there. Woohoo! We're going to finish. How many different sums of money can be made from 2 pennies, 3 dimes, and 2 quarters? Okay, so it's in your pocket, you pull it out, you got 2 pennies. We should change that, eh? Nickels, because we don't even have pennies. Let's make this 2 nickels. 2 nickels. What's a penny? See, 5 years ago. What's a penny? Okay. So how many different sums can we make? So do you have to use all? Could you just use 1 nickel? Right? That's a sum of money, right? I can get 5 cents out of it. 1 nickel would be 5 cents. Okay, so we have nickels, dimes, and quarters. How many nickels can we have in the... So how many nickels do we have to choose from? 2. How many of them can we have? You could have 0, or 1, or 2, right? So that's the key, right? It's not just, oh, the 2 nickels can be arranged 2 ways, right? It's like, I have 2 nickels, which means I have 3 choices, right? I can have no nickels, or 1 nickel, or 2 nickels. Okay, so dimes, what goes in here? 4. Quarters? 3. Now, what's the problem with that? One of those arrangements, yeah?
If you had a 0, wouldn't it make everything 0?
Yeah, one of those arrangements is no nickel, no dime, no quarter, no money. So what do we got to do? But that's only one arrangement, right? So what are we going to do with this? Subtract 1. So these are the arrangements, but one of those arrangements can be done. All right, so what's that? 36, so 35. I'd throw this down to exclaim, but that would not be the wisest thing to do.